I think probably we can make a start. Right. So hello everyone, welcome to the IVM online webinar. And today we're very glad to have Dr. Shebha Anandhi Jegadeesan as our speaker. Shebha earned her PhD at the National Institute of Technology in India, where she worked on the magnetic nanoparticles for cancer treatment and MRI, using EPR to study their properties. And this expertise in spin systems led her to join Dr. Gunnar Mercer's group at the University of Konstanz in 2022. And since then, she's been developing pulse sequences and simulating steady-state pulse DNP. And this is what she will be sharing with us today. So feel free to make a start, Shebha, whenever you're ready.
Thank you, Yuji, for the nice introduction. I also thank the organizers for organizing this seminar series. I'm Shebha Anandhi Jegadeesan. I welcome you to my talk on the simulation of pulse dynamic nuclear polarization in the steady state. MAS-DNP is magic angle spinning dynamic nuclear polarization. It is a powerful technique to improve the sensitivity of high-resolution solid-state NMR. We all know that NMR is an insensitive technique, and we can improve the sensitivity of NMR by transferring polarization from an electron to the proton. I'm also sure most of you would be familiar with these expressions. The maximum polarization that we can transfer from the electron to proton is 658. This is the maximum enhancement we can get when we transfer the full polarization. And this is dependent on the polarization of electron and also on the population of the electron spins at thermal equilibrium, which is given by this expression. The polarization of electron depends not only on the temperature, but also on the external magnetic field. Commercial MAS-DNP instruments are equipped with gyrotrons that generate continuous microwave. And here's the schematic of continuous wave DNP. When we apply continuous microwaves on the electron with low power for a long time, there is low polarization transfer from the electron to the protons that squirts nearby, and there is a slow transfer from the first proton to the next proton. So, likewise, this polarization is passed on to the bulk nuclei through spin diffusion process. And in the end, when we measure NMR, we get a signal that's hyperpolarized. Transitioning from continuous wave to pulse DNP. We need this transition because continuous wave DNP might not be the most efficient method to transfer polarization from electron to proton. With pulse DNP, this may be made efficient for polarization transfer. We can utilize the spin dynamics to improve the efficiency and flexibility. With pulse DNP, rapid transfer from short-lived photoexcited triplet states shall be made possible, whereas with continuous wave, this may not be achievable because we need to apply microwaves for a very long time. Also, pulse DNP is not dependent on the saturation, whereas for continuous DNP, we need to saturate the EPR spectrum. And with pulse DNP, we may enable DNP with a low duty cycle. So instead of waiting for a very long time to transfer polarization with pulse DNP, we can not only get high efficiency, but also do experiments faster. The only limitation with pulse DNP is getting a high power microwave source. This is available for low magnetic fields, but when we go to high magnetic fields, we have this limitation. We need to build amplifiers that can produce high fidelity pulses of high peak power. Coming to pulse DNP, here's the schematics for pulse DNP. There are different types of pulse DNP sequences we explore, and this block can be any of these pulse sequences. So now when we apply a pulse sequence, DNP pulse sequence on the electron, here the polarization transfer is slightly different from continuous wave excitation because we also wait for the electrons to come back to equilibrium. And this space here indicates that. And after every application of the DNP pulse sequence, there is a little bit of polarization transfer from the electron to the nearby protons, and it is passed on to the bulk nuclei slowly. And in the end, when we do NMR detection, we get a signal that's improved in sensitivity. Normally, we test all of our samples with this sample trityl OX063 in deuterated glycerol, deuterium, and water in the ratio 60, 30, and 10. This is percentage by volume, and we do the experiments at a sample temperature of 80 Kelvin. Here some example for pulse sequences are shown. Nuclear spin orientation via electron spin locking, novel. With this pulse sequence, DNP experiments have already been done in 1988. This pulse sequence was extensively later on investigated by Jane and Mathis in the Griffin group. This pulse sequence consists of a 90-degree flip pulse followed by a spin lock along the -y axis. The duration over which the microwaves are on is the contact time. In the end, we have an optional flip back pulse. This is because instead of waiting for the electrons to come back to equilibrium, we can also apply a flip back pulse for the electrons to bring them back to equilibrium and repeat this process. The matching condition for novel is given by this expression. Omega effective is the effective angular frequency. Omega 1s is the electron nutation frequency, otherwise known as Rabi frequency. The capital omega is the microwave resonance offset. Novel is usually applied on resonance, so omega is 0, and the matching condition would be omega 1s equal to omega 0y. So the electron nutation frequency equal to the proton Lama frequency is the matching condition for novel. Time-optimized pulse, top pulse sequence, was explored for DNP by Kong and Mathis in the Griffin group. XIX DNP was first introduced in our group by Redrauto and Mathis. This was also later on investigated by Wheely. Two-pulse phase modulation. This DNP pulse sequence was also introduced in our group by Redrauto and Mathis. For top pulse sequence, this consists of pulse duration TP, over which the microwaves are on, followed by delay. This one unit is called one block, and the modulation time for this block is Tm. This unit is repeated m times to make up the contact time Tc, together with the modulation time. For x inverse x, as the name suggests, we are applying opposite phases. We are applying the pulse sequence with opposite phases. So the first phase is 0 and the next phase is 180. And we are repeating this for m times. For two pulse phase modulation, instead of 0 and 180, we can have any combination of phases. The phase difference between two pulses can be either 10 degree or 120 degree. It can be any phase difference. And all of these pulse sequences follow this matching condition, where omega m is the modulation frequency, which is 2 times pi over the modulation time Tm. Omega effective is the effective frequency, which is given as the flip angle over the modulation time. And omega 0y is the proton Lama frequency. K and L can take values plus or minus 1, plus or minus 2, so on. And K can take these values. L and N can take values plus or minus 1. From this matching condition, we can find out where we can see DNP. For example, at a particular microwave resonance offset, when we apply a particular nutation frequency. But though we can find where the DNP can occur, we cannot get information about how much DNP efficiency we would get. So in order to find out, we either have to do simulations or do the experiments. So I'll give an example of how a pulse DNP experiment is done. So this is our lab at the University of Konstanz, where we do pulse DNP experiment. This is in Bruker EPR console. This is the microwave bridge. This is the red box here is the NMR console, where we can do radio frequency, excitation, and detection. This is a former PhD student. He's doing tuning and matching for the NMR. We have an endo probe for proton detection. So this probe has an external tuning and matching box, which was made at the university workshop. This line is the helium transfer line, liquid helium dewar. And we also have a centralized facility where if the helium evaporates, it's collected and liquefied later on. This amplifier is a 50-watt amplifier at Q band. It can produce a maximum nutation frequency of 38 megahertz. Here, different EPR bands and corresponding magnetic fields and the proton Lama frequency and the microwave frequency are given. For X band, at a magnetic field of 0.34 Tesla, the proton Lama frequency is 15 megahertz. So in order to do a novel experiment, the matching condition would be getting a nutation as high as 15 megahertz. And this is possible at X band. For Q band, at 1.2 Tesla, the proton Lama frequency is 15.1 megahertz. So here we can see we can only go to a maximum nutation of 38 megahertz. So we cannot do the novel experiment at 51 megahertz, but we can do all other high field compatible pulse sequences, stop, XX, TPPM, and so on. Few other people in the world would have a Q-band DNP instrument where they can have high power, and for them, achieving this nutation is possible. At W-band, at a field of 3.4 Tesla, the proton Lama frequency is 143 megahertz. So far, the maximum nutation that is achievable at W-band is 42 megahertz. So we are still very far from the matching condition for novel at W-band. And for J-band, at 9.4 Tesla, the proton Lama frequency is 400 megahertz. So far, Pulse DNP is possible at X, Q, and W bands, and for J band, the devices are under construction. So at University of Konstanz, we can do experiments, DNP experiments at X and Q band. Our collaborators at the University of St. Andrews have a W band instrument. It is a home-built broadband, high-power, pulsed EPR spectrometer called HYPER that is adapted for DNP measurements at W band. It's a unique instrument. They can go to a very high peak power of 1.3 kilowatts, and they have a very broad bandwidth of 1 gigahertz. Here I show simulation versus experiment. Previously, simulations were available only for single polarization transfer from one electron to two nearby protons. And all of these simulations were done using SPINach, which is a simulation spin dynamics simulation tool, numerical simulation tool. And after optimizing different parameters for the pulse duration, for the phase, for various electron nutation frequencies, and for different microwave resonance offsets, some conditions were identified for the experiments, which also worked out very well in the experiment. Here, two examples are shown, one with XIX pulse sequence and one with TPPM. Here on the y-axis is the electron nutation frequency. This is a parameter scan. On the x-axis is the microwave resonance offset. This horizontal line is at 18 megahertz, at which this experimental field profile was measured. Here we can see that these DNP conditions where positive enhancement and negative enhancements appear is also observed in the experiment. The simulations predicted the experiment very well. Also for TPPM, at this horizontal line, at 33 megahertz, this was the field profile. We get maximum DNP close to 0 megahertz as predicted. And the phase was optimized to be 120 degrees. So in the experiment, from the optimization, this was also close to the value that was obtained from the simulations. So now single transfer simulations were useful for identifying experimental conditions, but there were still deviations between the simulations and experiments. Here, a contact curve. The contact curve is shown for different pulse sequences. From the simulations, the maximum DNP was obtained for TPPM pulse sequence, which is also true for the experiment, but the rate of transfers are very different as we see from the simulations. XIX and XIX pulse sequence shown in purple and top at 33 megahertz, the red one, is very slow in the single transfer, whereas in the experiment, they are as fast as TPPM. And top at 18 megahertz is lower, but it's not as low as the single simulations predict. So we can see that there are still many deviations. The intensities are incorrect and the transfer times are not as we see in the experiment. And moreover, with the single transfer simulation, we cannot repeat the repetition time profile. This repetition time profile, the optimal repetition time is unique for each pulse sequence. And with the single transfer simulation, we cannot find out what this could be for each sequence. So this shows that we need better simulations to better capture the experimental features that we see. And here is an attempt to that. Here, the single polarization transfer with novel pulse sequence at X band is shown for different protons. Here, this proton is very close to the electron. The red one is for the proton that's further away. Third one is still far, and fourth one is the farthest. The proton that's close to the electron during the first time excitation of microwaves gets the maximum DNP transfer, whereas the second proton receives less, and the third and fourth proton receives even less. So in the experiments, we don't do one-time excitation. We repeat this process. The microwaves are stopped at 2 microseconds, and this is repeated with a repetition time of 1 millisecond. Here, 8 transfers are shown. These peaks here are the duration over which the microwaves are on, and these horizontal regions are the duration for the electrons to come back to equilibrium. So we can see that for each proton, how the buildup is slowly increasing. After 512 transfers, the first 3 protons, the proton that's very close as well as up to the third proton, they already reached the steady state here. There is no change in the system after this point, whereas the fourth proton is still getting there. And steady state is an equilibrium state. After the application of microwaves and the relaxation, all of the spins are at the same state. And the current complexity numerical simulations are all spins of a very large spin system, and their interactions have to be modeled. And it can take seconds to reach a steady state. Even at half a second, here the fourth proton has not yet reached the steady state. So the brute force simulation approach is computationally very expensive. Instead of calculating all of these points in between, we have a solution to calculate the steady state without having to go through all of these points. Periodically driven dissipative linear systems, in our case DNP pulse sequence followed by relaxation, these systems have a steady orbit. Steady orbit is a periodic trajectory to which system dynamics eventually converge, and stroboscopic steady state is a state at a given point on the steady orbit. And this is the point that we measured in the experiments. So here, 3 algorithms are given with which we can calculate the stroboscopic steady state. The spin dynamics under the influence of DNP pulse sequence is described by the equation of motion for the density matrix rho, where rho is the state of the spin system. The time derivative of rho is given by this expression. H0 is the Hamiltonian commutation superoperator that is time independent. This is the part of the Hamiltonian that we cannot control. H1 of t is the time dependent Hamiltonian. The effect of microwave pulses are described by this Hamiltonian. R is the relaxation superoperator. For the steady state, this expression is equated to 0 and rho is replaced with rho infinity. And rho infinity is the steady state that we calculate with these 3 algorithms. The first one is propagator squaring. With propagator squaring, we start at thermal equilibrium and square the propagator. Here the propagator is under the influence of the DNP pulse sequence. We square the propagator till the steady state is reached. So here we are not going through all of the points as in brute force propagation. The time evolution is doubled with each step. So this is better than brute force propagation, but it's still computationally expensive. The next one is the effective Hamiltonian method. Here, H with the bar is the effective Hamiltonian and R with the bar is the effective relaxation. So in order to calculate this term, we need to take the logarithm of this propagator. This is calculated using inverse scaling and squaring method. The inverse times vector operation strains the IEEE floating point precision. The numbers are stored in a computer in 2 to the powers. So for a simple spin system, this number is 2 to the power minus 53. The moment we include additional spin, this number becomes larger. And when we keep on adding more and more spins, the number becomes even larger. So there are so many decimal points in this storage unit. So there is a point when the computer cannot fit this number anymore, and we run into a numerical problem. Effective Hamiltonian method works very well for up to 3 spins. And when we add the 4th spin, the calculation crashes. So we do not recommend this method for computation of the steady state. The next method is Newton-Raphson. All of us must have studied Newton-Raphson method in calculus and numerical methods where we find the roots of a real valued function. So this is the function for which we need to find the root. We start with an initial guess, which is x0. F of x0 is the function. We take the derivative of this function, which is this tangent. This makes an intercept on the x-axis at x1. This is the point for next approximation. So we take the derivative of this function f of x1. We repeat this process till we find the roots. And we can see that within very few steps, we have arrived at a solution. We have used this method to calculate the Newton-Raphson algorithm to calculate the steady state, and this is the first time we are doing this. Here too, we start with an initial guess. The function of interest is rho, which is the state of the spin system. We repeat the iterative steps till we see convergence. And here, by convergence, what I mean is that when we calculate the state of the spin system and go forward towards a steady state, the propagator stops changing, and this is when we know that we have reached the steady state. Newton-Raphson method is numerically stable. It is also much faster than propagator squaring. So these propagators, these algorithms have been implemented in Spinach by our collaborator Ilya Kuprov, and they are available for use to everyone. So I mentioned that Newton method is better. Here's the performance check for the stroboscopic steady state algorithms, Newton and squaring method. On the y-axis is the wall clock time, which is nothing but the computation time. On the x-axis is the state space dimension. So when there are multiple spins and the interspin correlations are increasing, the state space dimension becomes larger. We have 10 spins in our system, 1 electron up to 9 protons. And we can see that as the state space dimension becomes larger, Newton method is 3 times faster than the squaring method on the graphic processing unit GPU. Here another comparison is shown with Newton method on GPU versus CPU. Here too, as the state space dimension becomes larger, the computation time on the graphic processing unit is 6 times faster than on the central processing unit. So we not only recommend the Newton method for calculation of the stroboscopic steady state, we also recommend using the GPU when you have many spins in your spin system. So now that we have a method to calculate the steady state, what are the next things that we need to keep in mind? Relaxation parameters are very important to reproducing the experimental results. And the first thing that we consider here is the proton longitudinal relaxation time T1n. Experiments have been done already in 1972 to calculate the proton, to calculate the relaxation rate of the proton that's close to an electron. Here, a single crystal is shown, ytterbium doped in yttrium ethyl sulfate. So ytterbium is the paramagnetic site, and the proton that's of interest is H1W7. The relaxation rate of this proton was experimentally measured. We can also calculate numerically, we can also calculate this relaxation rate from the description given in Abraham and Goldman using this expression. So the proton that's close to an electron relaxes faster compared to the proton that's far away. And this is dominated by the longitudinal relaxation time of the electron. So T1n depends on T1e. It also depends on the external magnetic field and the dipolar field. The dipolar field comes from the electron-nuclear dipolar coupling. So this is the expression to calculate the electron-nuclear dipolar coupling. So all of these are constants, and this majorly depends on the distance between the electron and proton, the dipolar distance, and the orientation of this dipolar vector with respect to the external magnetic field. So this coupling goes into this calculation to calculate the dipolar field. And when we substitute this here, T1n is proportional to r to the power 6 because of this square. And all of you would know this expression, nuclear magnetic resonance field. So this is also going into the calculation for T1n. So we wanted to use this calculation to calculate the T1n for the proton that's close to the electron, as well as for the electrons, for the protons that's far away from the electron. So in order to do this calculation, we need to confirm that we are doing the calculation correctly. So we use this formula to do this simulation. And now we are confirming that the calculation that we do is correct. And we use this formula for our spin system. And this term is coming from the electron polarization term. Hyperbolic secant square is 1 minus hyperbolic tangent square. So here is how we calculated the orientation and distance dependence of T1n. This expression comes from Abraham and Goldman. And this part, we also added the effect of the bulk nucleus here. So as we R is the electron-proton distance. So when the proton is close to the electron for different orientations, 0 to 90, we can see how T1n changes. And as we approach the bulk, as we go further away, as the proton is placed away from the electron, we can see that the T1n comes to takes the bulk value. So this expression is included so that as the proton is placed far away, it can take the bulk value. In spinach, we have different powder grid orientations. For our simulations, we used 800 powder grid orientations. And at 3.5 angstrom, T1n, at 3.5 angstrom, T1n changes as shown here for various orientations. And the interesting point here is that at the magic angle of 54.7, even for a proton that's very close to an electron, we get the bulk T1n value. So as shown here. And R1n is the inverse of T1n, which is the relaxation rate, and this changes with orientations as shown here. So now that we have the calculation for T1n with respect to distance and orientation, the other parameters, the other relaxation parameters are given here. The electron longitudinal relaxation time, T1e, come from the experiments. It's taken as 1 millisecond. T2e is the electron transverse relaxation time. This is taken as the phase memory time from the experiments, which is 5 microsecond. For T2n, the nuclear transverse relaxation time. So here we assume the dominant mechanism is the proton spin flip-flops, even for the protons that's very close to the electron. And here we consider this as the spin echo decay time of 20 microseconds. And this seems to work for all of the simulations. The bulk value of T1n come from the experiments. It is 52 seconds at the Q and W band and 26 seconds at X band. The spin system that we consider here is very simple. It consists of just 1 electron and 1 proton. And when we do the calculations in the steady state, when we put in the right set of relaxation parameters, this simple spin system seems to be enough. So in addition to one electron and one proton spin system, we also do ensemble averaging over the electron-proton distances. This is because in realistic situations, one electron is normally surrounded by thousands of protons. So we take shells of protons around the electron and do spherical integration using this expression given here. Here, the radial part of the integral is evaluated using Gauss-Legendre quadrature. R minimum is taken as the effective distance of 3.5 angstrom and R maximum is taken as 20 angstrom because at 20 angstrom for all the orientations, T1n approaches the bulk value. Further, we also take distributions over electron nutation frequencies. This is because the magnetic field component of the microwaves that the samples experience is not uniform throughout the sample. And even if you try to make the field homogeneous, there would still be some inhomogeneity that the sample sees. In order to account for this, we are also doing averaging over the electron nutation frequencies, which we call the B1 ensemble. Here, the first results are shown with the steady state simulations. Field profile with XX DNP pulse sequence is shown. This is the single transfer field profile that was used to identify the experimental DNP conditions. So we can see that the simulation predicted the DNP at these offsets, which is also true for the experiment, but we can see that the intensities are not the same as we see in the single transfer. The shape of the field profile is very different. The peaks are all pointy, and this is not what we observe in the experiment. Now, when we do the simulation in the steady state, even with a single parameter set of just one electron and one proton, we get the shape of the field profile as we see in the experiment. When we include the distance ensemble, the intensities of the peaks further off resonance match the experiments very well, except for this central region. With the distance ensemble, when we also include the B1 ensemble and do the integration, we get all of the peaks as we see in the experiment. This is because, especially for this region, this can be explained with this figure. This is the single transfer simulation. On the y-axis is the electron nutation frequency. So these peaks are broad. So for a large range of B1, these conditions are DNP active, whereas these two spots are active only for a small range. So when we include a large distribution in B1, we lose the efficiency, DNP efficiency in these regions. And this is what we see in the experiment, also observe in the simulations. Now we can not only simulate the experiment better, we can use the simulations to understand what's going on in the experiment. Here the field profiles with XX DNP pulse sequence at W band is shown. This is the optimization of pulse duration at different microwave resonance offsets. The contact times are taken such that, or calculated such that it's close to 360. So it's ranging from 340 to 370 nanoseconds. And now when you look at the steady state simulation and experiment, once again, they are matching very well. All of these regions where we see the DNP active conditions are also observed in the experiment. And these nodes where you do not see DNP is also reproduced very well in the steady state simulations. The W band experiments were done at the University of St. Andrews by our collaborators, UG and Graham. For this particular steady state simulation, the computation time took only about an hour. And here the distance ensemble was sufficient. This is because here single transfer simulation is shown for varying electron nutation frequency. And for these DNP conditions, this is for a particular TP. And here we can see that for these vertical stripes, they are active over a long range of B1. And there are no spots that's only active for a small range of B1. So for this particular simulation, the B1 ensemble was not required. But for all of the simulations, we also included the B1 ensemble. Here, the optimization of repetition time is shown. The simulation of the optimization of repetition time is only possible in the steady state and not with single transfer simulation. Here, the experimental optimization is shown for top XX and TPPM pulse sequence. The parameters at which the optimization was performed is given in the table. For top pulse sequence, the optimal repetition time is about 100 microseconds. This is limited by the duty cycle. For XX pulse sequence, the optimal time is about 200 microseconds, and for TPPM, this is about 1 millisecond. So this is also what we observe in the steady state simulations. We are able to reproduce this behavior. At X band with normal pulse sequence, after applying the flip pulse, when we do a spin lock and repeat this process and acquire, this black curve is what we get for the repetition time optimization. And after the spin lock, when we apply the flip back pulse for the electrons to bring back to equilibrium, we see that in the experiments, there is an improvement in DNP efficiency along with the shift with the optimal repetition time. This behavior is also very well reproduced in the steady state simulation. Here, the polarization transfer during the DNP sequence is shown. This is what we call as the contact curve. In the beginning, it was already shown that the single transfer simulations don't predict the experience very well. The transfer times are incorrect. Now, when we do the simulation in the steady state, we see that the transfer times are matching as we observe in the experiment. TPPM gives the highest, has the highest transfer, which is also observed in the experiment. X-axis and top pulse sequence at 33 megahertz nutation is also as fast as TPPM, as observed in the experiment. And top at 18 megahertz, the blue curve has a slow transfer time. So we can simulate this very well, but we do see some differences. For example, with TPPM pulse sequence, we see that the expectation value of phi z is decreasing in the simulation, whereas in the experiment, it's increasing. This we account because our spin system is very simple. We only have one electron and one proton. When we include the spin diffusion process and the effects of multiple protons, maybe we can reproduce the experiments even better. But already with one electron and one proton in the steady state, we are capturing all of the features that we should see in the experiment. So the steady state simulations are doing their job very well, even for this simple spin system. And in addition to that, we also see there's a crossover between X-axis pulse sequence, the purple curve and the red curve with top at 33 megahertz. This crossover is also very well reproduced in the steady state simulations. Here, the electron nutation frequency dependence is shown for with X-axis and top pulse sequence. This is single transfer simulation, the optimization for various electron nutation frequency. At these arrow points, the experiments were measured as the nutation was increased from 7 to 36 megahertz. The simulations predicted that for both X-axis and top pulse sequence, there was an improvement in DNP efficiency with increase in electron nutation frequency, whereas in the experiment, that was not the case. For X-axis, there was constant DNP enhancement for all of these increasing in nutation frequency, whereas for top, there was an improvement in efficiency with increasing nutation frequency. Also in the experiment, the repetition time had to be optimized for each nutation frequency. As when going from 7 to 36 megahertz, the repetition time for X-axis was optimized from 51 to 306 microseconds, whereas for top, for all of these nutation, it remained a constant about 153 microseconds. So now when we put in these repetition times as observed in the experiment in our simulation, we reproduce the effect of nutation frequency as well. For X-axis, we see constant enhancement. This is also what we see in the steady state simulation. For top, there's an improvement in DNP efficiency. This is also what we observe. In addition to this, we also see there's a shift in the microwave resonance offsets, which is going towards the left for X-axis with increase in nutation, whereas for top, it's in the other direction. We are reproducing all of these features as we observe in the experiments. Here, pulsed versus continuous wave DNP is shown. A lot of people have this question, pulsed versus continuous wave, which is better? So to answer that question, this steady state simulation is done with equal average power. Continuous wave, with continuous wave irradiation, a novel pulse sequence at nutation of 15 megahertz, both of them have the same power. And here we can see that with novel pulse sequence, we get DNP that's higher than the continuous wave for the same average power, even without the flip back pulse. Now, when we apply the flip back pulse, the DNP efficiency improves even further. So it's clear that the pulse DNP is better than continuous wave DNP with the same average power. So we can not only do efficient transfer, we can also do this faster. So we can reduce the duty cycle. And at X-band, people prefer to do continuous wave DNP because they do not have the electronics for pulse DNP. And this is okay at X-band, also at Q-band. But as you go to high fields, if you continuously irradiate the sample with microwaves for a long time, this can lead to sample heating. So with pulse DNP, we also avoid this disadvantage in addition to transferring polarization efficiently. And here it's shown that novel is efficient than continuous wave, but this may not be the most efficient pulse sequence. There are other pulse sequences that people are trying to find, and we are also doing the same. Okay, so far we saw DNP by different types of pulse sequences, also pulse versus continuous wave. Here DNP by adiabatic passage is shown. The pulse sequences that we saw previously, TOB, X-axis, TPPM, there's also another pulse sequence called beam here. All of these pulse sequences come under sudden experiments. These are diabatic pulses. This is because when we apply these pulse sequence, there is sudden rotation of the density operator around the Hamiltonian. And the evolution of the spin system is determined by this Hamiltonian. Only the strongly coupled spins can follow when we apply these pulse sequences, and the weakly coupled ones cannot follow during this sudden rotation. Here the contact curves are shown for top XX and TPPM sequences. The expectation value of IZ is normalized. So with these pulse sequences, also novel and pulse solid effect, the maximum polarization that we can transfer from electrons to the protons is only 50% even after powder averaging. But by doing an adiabatic passage, we can overcome this limit and reach a maximum expectation value of 1 by doing either a frequency sweep or field sweep through the matching condition. When we do an adiabatic experiment, we are dragging the density operator together with the Hamiltonian. If the Hamiltonian changes slowly and continuously, the spin system follows. So during this process, not only the strongly coupled spins, even the weakly coupled spins would follow when we sweep through the matching condition. Here the simulation is shown at 3.4 Tesla on resonance. This is with electron nutation frequency matching the proton Lama frequency condition. At W band, we do not have such high powers, but when we are at this condition, this is the adiabatic passage that you would see, and the maximum polarization after normalization would be 1. At Q band, you would see the same passage when we are at a nutation frequency of 51 megahertz, which is equal to the proton Lama frequency, and at X band, you would see the same passage for 15 megahertz. So the only disadvantage with adiabatic passage could be that we should apply this for a long time. And frequency sweep and field sweep can be alternately done. One can be used in place of the other. At low magnetic fields, field sweep is all right. But as we go to high fields, sweeping the field is not advisable. Their frequency sweep could become advantageous. So far, DNP in the literature has been reported with linear pulses. Here some examples of field profiles are shown. These are experimental field profiles by Khan, and this is experimental field profile by Tan. There are different types of solid effect that you could see with a chirp pulse, linear chirp pulse. The first case is the integrated solid effect, next stretched and adiabatic solid effect. All of them follow the same matching condition. So we saw in the beginning the condition for novel. So this can also be called solid effect condition depending on the value for omega, capital omega, and omega 1s. When we are on resonance, so this equation can omega 0y is this radius. And when we go through the semicircle, we go through different conditions. When we are on resonance, we match the novel condition. And when we are off resonance, further off resonance, we go to the classical DNP condition. So when omega 1s is very large, so this should be equated to omega 0y. And when the capital omega is much greater than omega 1s, we are at the solid effect condition. So integrated solid effect at W band, in order to see this effect, we need to have a large bandwidth. So at W band, we need to have a bandwidth of 300 megahertz so that we could sweep through double quantum 0 and 0 quantum transition regions. With the chirp pulse centered on a resonance, when we sweep through all of these three conditions, we see the integrated solid effect on resonance. Integrated solid effect is direction dependent. When we do a positive sweep, we see positive enhancement. When we do a negative sweep, we see negative enhancement. With the same large bandwidth of 300 megahertz, when we center the chirp pulse above the double quantum and sweep or the 0 quantum and sweep, we get the stretch solid effect. This we see further off resonance. And stretch solid effect is not direction dependent. Either you do a positive sweep or a negative sweep, you see enhancement on the same side. The next, the next one is the adiabatic solid effect. This is having a narrow bandwidth. We taking a narrow bandwidth, we sweep through one of the double quantum or 0 quantum regions, and then we get a DNP efficiency that's much better than with the normal solid effect condition. So on resonance, when we sweep through resonance, adiabatic inversion occurs, and at dq and zq, the polarization transfer happens by adiabatic passage. We have explored shape chirps for DMP for the first time. Shape chirps have been used in NMR. Here, an example is shown, which is the Wurst chirp pulse. Wurst stands for wideband uniform rate smooth truncation. It was first used for broadband excitation. It's also been proven useful for heteronuclear decoupling. The amplitude profile of the Wurst chirp pulse is given by this expression. The amplitude depends on the bandwidth, omega BW, also on the capital T, which is the total duration of the pulse. Small t is the time units that comprise the individual units throughout the chirp pulse. And A is the amplitude profile that gives the effect of shaping, which we call the smoothing factor. Phi is the phase profile of the Wurst chirp pulse. This also depends on the bandwidth, the total duration, and the small time units that comprise the total waveform. Frequency is the time derivative of phase, which is linear for the Wurst chirp pulse. It is also a linear sweep. Frequency sweep is linear for the linear chirp pulse, which is equal amplitude throughout, and also for the smooth chirp, the frequency sweep is linear. For this shape, the edges are chipped off. So this is having a shape that's very different from the Wurst chirp pulse, and these they look like this because of the smoothing factor that we chose for the DNP experiments. Here, the blue curves are the real components of the waveform, and the red ones are the imaginary components. So as usual, we do simulations first in order to identify the conditions for experiment, and then we do the experiments. So when we started the simulations with the chirp pulses, we so we met with the complexity, which is the computation time. It takes a long time to do the simulation. This is because a chirp pulse has a complex waveform. In order to sample all of the points, we need so many points. We need at least 10,000 time steps to sample this full waveform. The Hamiltonian of pulse DNP experiments are not so complex. This is because this XX pulse sequence needs only 20 blocks per microwave irradiation, whereas a chirp pulse requires about 10,000 time steps. So the first thing that we tried is adaptive sampling. Instead of having equal number of points throughout the chirp pulse, if we reduce the points where we have less oscillations and include more points on the sides where there are more oscillations, we can reduce the total number of points. And by reducing the number of points, we reduce the computation time. The next thing that we did is approximation for Hamiltonian. We can use two different methods to calculate the Hamiltonian. And the first one is piecewise constant. The other one is piecewise linear. Normally, piecewise constant works faster. But the problem with this is it requires a large number of time steps. Here an example is shown for this waveform. On the y-axis is the amplitude. So in order to sample this waveform, we need to have so many time steps. And here the propagator is calculated per time step. And for all of these steps, the propagator needs to be calculated. And because there are so many steps, the calculation takes a long time. With piecewise linear, adjacent propagators have shared intervals. So because of this, piecewise linear can have less number of time steps, and it gives better performance in the end. Adaptive sampling, together in combination with piecewise linear approximation, saves computation time by an order of magnitude. Here, the results of DNP by adiabatic passage is shown with different shaped chirp pulses, linear, Wurst, and smoothed. This is the single transfer simulation, steady-state simulation, and experiment. In the single transfer simulation, we can see that with the linear chirp pulse, where we have equal amplitudes throughout, we see the integrated solid effect on resonance. And the next one is the green curve with the smooth chirp pulse. Here we are shaping the chirp pulse. So we are not efficiently sweeping through the double quantum zero and the zero quantum regions. So because of this, we lose the integrated solid effect on resonance. For Wurst chirp pulse, there is deeper smoothing, and since there is deeper shaping, we lose the integrated solid effect fully, and the effect of shaping is reflected in the shape of the field profiles very well. Now, comparing single transfer simulation to the experiments, we see all of these features in the experiment except for this portion, where integrated solid effect stands out way higher in the single transfer simulation. This is because when we apply the chirp pulse first and do the first transfer, integrated solid effect transfers very high in the beginning. After the relaxation for the second and third transfers, it's not as high as the first one. So that the transfer may be faster, but it's not as high for the consecutive steps. Whereas for the stretch solid effect, even though it's transferring very less in the beginning, after relaxation, it's not it's transferring slowly, but it's not losing much compared to the integrated solid effect. So it's catching up with the integrated solid effect in the experiment. And when we put in the same set of relaxation parameters as with XIX pulse sequence at the W band, so we are also reproducing this experimental behavior with the shape chirp pulses, including the integrated solid effect. These experiments were done at the University of St. Andrews by our collaborators UG, Hassan, Robert, and Graham. So once again, we show that the steady-state simulations reproduce the experiments very well. Here, the optimization of experimental parameters are shown at W band with the steady-state simulations. For the integrated and stretch solid effect, this is the optimization of repetition time. The maximum the optimal repetition time is here. Whereas in the experiment, with an average power of 2.6 watt, we are limited by the duty cycle. We can only repeat as fast as 2.5 milliseconds. So this is for us to check we are at the optimal point. So when we are limited by the duty cycle, we are at the optimum. So the next thing that we can optimize is the bandwidth. So for the stretch solid effect, the bandwidth is 300 megahertz. So as we reduce the bandwidth, we come closer to the adiabatic condition. So, and we can also see that the expectation value of IZ is increasing as we narrow the bandwidth, and it's a maximum at a bandwidth of 30 megahertz. So next, for this adiabatic condition, adiabatic solid effect condition, we optimize the repetition time again. And here too, we can see that the optimal point is even faster compared to the stretched and integrated solid effect. And here we are again limited by the duty cycle. So the maximum we can go here is up to 2.5 millisecond. And at 40 megahertz nutation, adiabatic solid effect performs much better than stretched or integrated solid effect. So experimentally, in order to do this full optimization in a single experiment session, after cooling the sample down to 80 Kelvin, it's not easy to optimize the repetition time, the bandwidth, and also the field profiles where we need to find out the offset for the repetition time and the bandwidth optimization. So it's a big process in the experiment. Here, simulations can be a useful guide to find out, to look as we can use the simulations as a guide to know what to look for in the experiment. And they're also useful for predicting the experimental performance, because we saw some examples where the simulations are matching the experiment very well. We can use the simulation to predict how the experiments could perform. And now that our with the steady state simulations, we can do different types of simulations with diabatic pulses, continuous wave, also with adiabatic pulses. We aim to use our steady state simulation to design efficient DNP pulse sequences. We are working on this and we are going in that direction. With this, I conclude my talk on the simulation of pulse dynamic nuclear polarization in the steady state. We recommend Newton-Raphson algorithm for simulating pulse DNP in the steady state owing to its stability and complexity scaling. We see very good agreement with experiments at X, Q, and W band with DNP pulse sequences novel, top, XX, and TPPM, even with a spin system of just one electron and one proton. We see very good agreement with the experiments when we include the electron-proton distance and B1 ensemble averaging. We showed that the steady-state simulations are also equally useful for DNP by adiabatic passage. We aim to use this as a powerful tool to design efficient DNP pulse sequence. We also encourage you to use the simulation tools if you're interested in pulse DNP. We also encourage you to use this if you're working with experiments where you need to find out the conditions for experiments. I would like to acknowledge the contributions of the people in this work. I thank Dr. Yuji Zhao, Dr. Hassan L. Mkami, Dr. Robert Hunter, and Professor Graham Smith for performing the W-band experiments at the University of St. Andrews, United Kingdom. I thank Professor Ilya Kupra from the Weizmann Institute of Science, Israel, for his contributions to the implementation of steady state in the steady state in spinach, also for the reduction of the computation time with adaptive sampling and the different approximations. Dr. Jennifer Mathis is my postdoc supervisor at the University of Konstanz, Germany. She is the principal investigator of this project. I also thank her for giving me an opportunity to work in this project through funding from Hyperion SFB 1527. I thank all the organizers of IVEM series for the invitation to the seminar, especially UG for the invitation. I thank all of you in the participants for your attention. Thank you.
Thank you a lot. Shebha, for this awesome talk. So it gives a very good review of from theory to implementation in computation and then to experiments. So it's very comprehensive. And now we're open for questions. So I will start with a very naive question. So you mentioned at some point the T1 of the proton at 80 Kelvin is about a minute. So is that measured with the radical or without the radical?
T1 of proton at 80 Kelvin.
Yeah.
Um,
So it's a
with
50
the
second
radical, with the radical, with the radical, yeah.
with the radical.
Yeah.
Okay.
Mm.
Because I have the experience that the T1 varies a lot. I don't know how that affects the experiment and simulation results.
Okay. Okay. The long measurement is without the radical, but it is also needed for the so T1 is needed for T1 near T1 T1E is needed for near T1N calculation, whereas the bulk nuclear relaxation that is so if there is a radical, then it would relax very fast. So in order to calculate it, actually maybe we don't add the radical there. Yeah.
Okay, so for the simulation, you put in the values.
Yeah. From the experiments.
Okay.
Yeah. Mm.
Great. Is there any questions from the audience? So the other question I had is for the integrated solid effect, where you show that after several different repetitive pulse sequences, I mean pulse shots, so the enhancement gets smaller. But so do you think it's related to the electron relaxation or
After
saturated? Or
the integrated solid effect, actually, so if we look at the magnitude itself, it's in the steady state, it's higher than the beginning. But then it's the difference between stretched and integrated solid effect comes from the first transfer.
right.
So when we apply in the beginning, so integrated solid effect is higher than stretched solid effect. So slowly
Right.
when it's building up, stretched solid effect catches up with the integrated solid effect.
Okay, so it's not integrated solid effect going lower. It's
Yeah.
increasing. Okay. Great. Okay, there are no more questions from the audience, so you must be crystal clear.
There's something in the chat.
So there's one question from Mayu.
Okay, why there are oscillations in the contact curves?
Yeah.
Okay. Um, so so the long oscillations are from the powder averaging. So we only have one electron and one proton in the spin system. So that is coming from that. Whereas if you're asking about the small oscillations, that's something very different because for TPPM it's very much visible, I think. Should I open the screen? Okay. So these small oscillations come because we are measuring we are going to the steady state at the end of each TPPM period. So here the contact time is increasing per block. So we are incrementing the pulse block over time and measuring it in the steady state. So when we do this, the direction of the electron magnetization is different for this block compared to the other block. So because of that, we see this oscillation because of the direction of the magnetization with the pulse block excitation. So in the experiments, because of multiple spins, we don't see this in the experiment, but in the simulations, it's clear because of that.
Okay, I think that answers the question. And there's one more question. So Newton method is very sensitive to initial conditions. What's the procedure to choose an initial condition?
Okay, so in the simulations, it's the thermal equilibrium. So we can start anywhere away from the thermal equilibrium. So if we start at thermal equilibrium, we would still be faster to reach the steady state. So you don't have to take extra measure if you don't know where to start. It's a thermal equilibrium.
If I may add to that, Mayur, of course, in magnetic resonance, you are never very far from your destination state. So the difference between a unit matrix and the steady state is, not very large, not orders of magnitude. And so essentially almost any matrix that's a valid density matrix is in fact an excellent initial guess. It converges within 2 or 3 iterations.
Hope that answered your question, Mario.
Yes, thank you. Thank you, Dr. Shebha, and thank you, Professor.
Cool. So have you thought about simulating for magic angle spinning condition? And do you think it's easy to implement, and how long in terms of the computation cost, will it be much more complicated than the static state?
It could be implemented in the future, but so right now, I didn't think about it. So maybe it's possible. I'm not sure how difficult it would be, but it is possible.
Okay. Okay, great. If there's no other questions, I think let us thank Shebha again for the very nice talk today. And I hope to see all of you in 2 weeks' time. Thank you all for joining us today. Bye.
Thank you. Bye.
Thank you.